Is everything okay? Can we start? Okay. So, welcome to the 20 minutes lectures corresponding to Auditorio 1 to be held in Auditorio 3. Okay. So, our first speaker is Ademir Pastor, who is going to talk about the global well-posedness for Benjamin Ono and dispersion generalized Benjamin Ono equations.
Okay, thank you. First of all, I'd like to thank you, the organizers, for the invitation to be here, especially Felipe's. By the way, this is a joint work with Felipe and Luis Farah. Okay, so we are interested in two Cauchy problems. Actually, global well-posedness and the energy space. The first Cauchy problem is associated with the Benjamin Ono equation, and the second one is associated with the dispersion generalized Benjamin Ono equation. Well, actually, the title of my talk should be global well-posedness for the generalized Benjamin Ono and generalized dispersion generalized Benjamin Ono equation, right? But for short, I omit the generalized. Okay, here H is the Hilbert transform. D beta is the Fourier multiplier with symbol psi to the power beta. Beta is a real number between 1 and 2, and K is an integer number greater than or equal to 1. Okay? Well, as Germain told you, this is a kind of interpolation between the BO equation and the KdV equation, right? Since for beta equals 1, we have the Benjamin Ono equation, and for beta equals 2, we have the KdV equation, right? Okay, so let me start with the BO equation. First, I apologize for the reference I didn't cite here, since I will not have time to discuss them. I'll set up only the most recent ones, the important ones to our work, okay? Well, we have a global well-posedness in the case if K equals 1, global well-posedness in HS for S here 1 greater than 1/4. It was proved by Buick and Planchon in 2008. And we also have global well-posedness for S greater than or equal to 0. And it was proved by Ionesco and Kenny in 2007 and Molinet Piller in 2012. Actually, these three results are a little bit different in what concerns uniqueness and continuous dependence upon the data. Okay, but all three results proves global well-posedness in the energy space. Okay. For K equals 2, you also have global well-posedness in HS for S greater than or equal to 1/2. This is Kenny Takaoka result. Also, this result includes the energy space. The energy space here is just the H 1/2, right? Okay, so first let me recall the critical Sobolev index for the Benjamin Ono equation is Sk 1/2 minus 1/k. Okay, so K, if K is equal to 2, we have Sk is equal 0. So K2 is the critical. I mean L2 critical, mass critical. Okay. So if K is greater than 2, we are in a supercritical regime, so things change a little bit. Actually, we have global well-posedness only for small initial data. As far as we know, we have global well-posedness only for small initial data. This was proved by Molyneux and Ribot. And we have global opposing HS for S bigger than or equal to 1/2. And we also have global opposing for small initial data if for K greater than 3. Sorry. If S is bigger than the critical sub-level index. Okay? Well, so as you can see, we have global opposeness in the energy space in the case K equal 1 or 2, but we do not have global opposeness for arbitrary large initial data for K greater than or equal to, right? So this is our main concern in this work is to give a criteria how small the initial data should be. Okay? Well, first let me recall the local opposeness for S for K bigger than 2. This result was proved by Molyneux and Ribot. If we assume these conditions, then for any initial data U0 in ATS, there exists a time. This time of existence depends only on the norm of the initial data, and a unique solution to our problem 1. Okay. Moreover, the flow map is Lipschutz unbounded, etc. Okay. So once you have this local opposing result, what you need to prove to get a global result? Since the existence time depends on the normal initial data, you only have to get an a priori estimate for the solution in the energy space. Okay? Well, how we get such a priori estimate? The method we use is the usual one. We just use two conserved quantities, the L2 norm, the mass, and the energy. So since the L2 norm is conserved, we only need to get an a priori estimate for the 1/2 derivative. To do so, we just write the 1/2 derivative using the energy and use the Galliard-Nirenberg inequality, and you have this inequality. So if the initial data is small enough, you can use a standard argument and prove that the solution remains bounded. Actually, this is the proof for small initial data. Okay? So the method we use to give a criteria how small the data should be was introduced by Ken and Merlin and Homer Rudenko in 2008 for the NLS equation. Well, we have also some applications to the KdV equation and the Zakharov-Kuznetsov equation. We have proved a similar result. The idea is the following. Here, we have a constant appear here. This constant appears from the use of the Galliard-Nirenberg inequality. In conclusion, the smallness of the initial data is closely related with the constant appearing in the Galliard-Nirenberg inequality. Okay? So, the smallness of the initial data should be related with the best constant in the Galliard-Nirenberg inequality. And the idea is to use the Galliard-Nirenberg inequality using the best constant. Here is the result. It was proved by Angulo, Bona, Linares, and Alon. So for any k greater than 0, the Galliard-Nirenberg inequality holds, and we have the best constant given explicitly. Okay? Moreover, you have this function appearing here is Q, is the ground state solution of this equation. Okay? Actually, the uniqueness of this equation, solution, the ground state for this equation was proved for the ABO equation by Emil Tolan and quite recently by Frank and Lesman. Actually, this paper will appear this year or next year. Okay? So now you can state our result. Assume we have initial dating h1 half. If it satisfies such a condition like this one, if in addition satisfies also this condition, then as long as the solution exists, the solution satisfies the same condition. Okay? So since the L2 norm is conserved, this quantity is bounded by this divided by this. Okay, so we get an a priori estimate. The proof is simple. We'll just use the inequality, the Gagliardi-Lamberg inequality, but now using the best constant. It's up here. And write now let's define a new function x of t and define these two constants, and then you have this inequality. You just define now a function f by this expression. We observe this function has a local maximum. Actually, the graph is something like that. If you assume that these two inequality holds, I mean, here you have x0, it's the maximum. Here is the maximum value, f of x. If you assume that the solution, the initial data satisfies this condition, then the continuity of the solution will imply that the solution remains bounded. Okay, actually this is the proof. But if you take a look at these two conditions, and using this inequality, just a calculation, this equality is just a calculation, we see that these two conditions are exactly these two ones here. Okay, it's just a calculation. Okay, so this is the proof for the Benjamin equation, right? As a corollary, so we can prove that the H1 local solution is actually a global solution. Why? We have to restrict ourselves to the case k greater than 5. Yes, because let me recall here from theorem 1, we do not have a local L-Posner in the energy space for k equals 3 or 4. Okay? At least in this situation, the existence time depends on the norm of the initial data. Actually, we do have local L-Posners in the energy space, but it was proven recently by Vento, but the time of existence does not depend on the norm of the initial data, it depends on the initial data itself. Okay. So, however, our priori estimate holds true for any k. So once you get a local L-Posner, if the existence time depends on the initial data, you have global L-Posner. Well, now let me pass to the Spiriton generalized Benjamin equation. The idea is almost the same. Here, we restrict ourselves to the case k greater than 2 beta. Actually, this is a supercritical regime. Here, the critical case is for k equals 2 beta. Okay. This equation has been treated by many authors: Kenny Ponce Vega, Coliander, Kenny Staffilani, Molinet Ribot, Hare, Gu, Kenny Martel Robiano, Fonseca Linares, and so on. However, at least we do not know any result concerning local Well-Posner in the energy space. So first, we prove a local Well-Posner in the energy space. Actually, this is not difficult if we use the linear estimate proved by Kenny, Martel, and Robiano in the critical case. Okay? So let me just give an idea. Actually, we have two more estimates. The first one is a maximal function estimate, and the second one is an estimate for the integral part of the integral equation. Well, how to prove this? It's quite simple. We have a maximal function estimate. It was proved by Kenny, Martel, and Robiano. So since you have 2 beta here and k is greater than 2 beta, you can interpolate this with the sub-level embedded, and we are done. So we have a maximal function estimate. For the integral part, we also use ideas introduced by Kenny, Martel, and Robiano. We just define the projection operator and define these two integrals. Here, t, capital T, is any fixed number. Just choose a number slightly greater than 1/2, satisfying this condition. Then we have an estimate using the first part we just have proved, localizing in space. This second inequality, this third inequality was proved by Martel, Kenny, Robiano. So we get this inequality. Now it's just an application of the Christian-Kazalev lemma. Okay, since this power here is negative, we can sum in n, and we are done. This is the proof. So here is our local Well-Posner result. So for U0 in the energy space, exists a T. Now such T depends only on the norm of the initial data, and a solution satisfying this is to estimate here. Okay? The flow map is continuous. The idea of the proof is the usual one. We just define this metric space and a ball, and with this norm. Okay? So to estimate the 8 beta over 2 norm, we just first the L2 norm, we just use a linear estimate, which was proved by Kenny, Martel, and Robiano. This integral estimate here, and just multiply by t to the power gamma for a small gamma, and we are this inequality. The same holds true for the beta over 2 derivatives. Okay, and we have the same kind of inequality. For the maximal function, we just apply our proposition, and for the linear part and the integral part, and we are here. Okay, the estimate for the derivative is similar. Just use linear estimate. So the fixed point theorem gives the result. How much? 2 minutes? Okay. Okay, so how to pass to global Well-Posness? Again, I will need to get a priori estimate. Here is Gallardo-Nirenberg inequality in this situation. The best constant, it's a little bit complicated, right? But we do have a best constant appearing here. Okay, so again, this was proved by Angulo, Bonner, Linares, alone, and the uniqueness was proved by Frank and Leslie. All right, so here is our result. If the initial data in the energy space satisfy this condition, if in addition satisfy this one, then the same holds true for the solution, right? The proof is exactly the same. We just write the d beta over 2 using the energy, use the best constant in the Galliard-Dielenberg inequality. Okay, so define the same function, and this function has a similar behavior as this one. Okay, so the continuity of the solution also implies that here is the x of t. This is bounded by x. Okay, actually this is the proof, and the theorem is proved. Okay, just to finish, let me do the following. We have left behind two open questions for this kind of problem, at least two, I mean. The first one is if the solutions obtained here has scattering or not, okay? Actually, this is a very interesting question, but we do not know how to. We need to work more on that to try to answer this question. And the second one is what happened if the initial data satisfies the opposite side here. Okay. Actually, this is the case for the Schrödinger equation. For the Schrödinger equation, we have scattering. For all solutions satisfy this condition, we have a similar result for Schrödinger equation. If the initial data satisfy this condition, we have scattering. Also, if this, the initial data satisfy the opposite side, the solution blows up in finite time. Okay, but here we don't know how to answer this question. Okay, so this is all. Thank you very much.